Just a quick housekeeping note. Please put your phones on silent if you haven't already. And if you need some sugar, I think there's some donuts out there. So if you need to wake up after lunch. Our next speaker, Max Pevzner. Full disclaimer: I've worked with him in the past. Really knows a lot about big data. He's worked on Hadoop infrastructure at companies such as Facebook, Zynga, and a few others I'm going to forget. But has done a lot of work in this experience and certainly educated me a lot about this space and how we're generally using it and are thinking about it incorrectly. So without further ado, I will turn over to Max. All right. Thank you, Dan. Thank you very much for coming to my presentation. I will be talking about big data and how we try to apply the security use case. So, brief introduction about myself. Dan did a wonderful job, so I'll skip the part about companies I used to work. What do I do for a living? I process very large piles of data into information. And we will get into the definitions of data versus information and why you want to do that during the course of this presentation. Another disclaimer, oddly enough, even though I'm speaking at a security event, I don't consider myself a security practitioner. Most of my background is in the data management, in sifting through data and processing it. And one of the facets of this data processing exercise is processing data that's security related, but that's not the only one I've done in the past. So, it's always good to have a definition. So what is big data? Unfortunately, today, big data is a buzzword. And everything that becomes a buzzword kind of loses a lot of meaning. For marketing reasons, anyone who does anything remotely related to data processing today calls their product big data because that's what sells. And can I blame the marketing folks for wanting to earn a living? I can't. So what I'll try to do, though, is I'll shoot them in the foot by trying to define what big data actually is and what big data technologies are and what they're good at and what they're not good at. And that would hopefully clear a lot of this sort of fuzzy cloud of marketing terminology by concentrating on what is the technology, how it works, what it does, what it's good at, what it's not good at. So, so one of the things I'd like to start with the word data and define, like everyone intuitively knows what data is. Data is usually raw. A log that comes out of a firewall or a web proxy, that's data. Now, if you have processed it into a nice report that is easy to look at, that's information because it's actionable, it's apparent, you can easily look at it and start making decisions and reasoning about things. But if it's just a big pile of bytes somewhere, it's data. And so my informal definition is information is data that's been processed and made ready for consumption. One analogy that I like to use is that data is like raw vegetables and raw food that we just brought from the store. Generally, we don't eat a lot of that. We'd have to cook it first. So information is the cooked meal. Data and its degree of structure. So there's a lot of talk about semi-structured data, strongly structured data, and a part of this big data technology stack and universe is ability to work with data that is not very strongly structured. So strongly structured data is something that has regular, well-defined data types like we would, for example, in the relational database. In the relational database, we typically define the data types for all the columns, for all the attributes, and everything is well known and well defined what goes where and what it should be. In a lot of the traditional software programming, also we define the data types for, in strongly typed languages at least, we define the data types for our variables and we know what should be there.
So that's strongly structured data, because it's very well defined what should be in those containers that hold that data. Semi-structured data is things like machine-generated logs. For security practitioners, you can think about your favorite firewall log, web proxy log, Active Directory log, any other log. Why are they semi-structured? They do have a structure. After all, if it's a log, there is some computer program somewhere that uses some flavor of printf or sprintf or something like it to generate this log. There's a finite number of those statements. There's a finite number of different logic combinations that will generate that. So it has structure, but this structure is not readily usable for comprehending it. It makes things a little more difficult. By just looking at the log, you can't really say right off the bat what's going on. So, and it's a little more difficult for a computer program or a script to be dealing with this type of data, semi-structured data. Because if everything is strongly structured, it's pretty easy. You just pick it, you do something with it. Practically unstructured, I would consider natural language text like a novel practically unstructured, even though the natural language has its own structure. At this day and age, we're still not very good at being able to operate on it using computers. So for practical purpose, I consider it virtually unstructured. And something is truly completely unstructured data is something we don't understand. There may be a structure to it, but we don't get it. So other than theory of chaos and theoretical mathematics, it's not really useful for practical purposes. So unless someone's an academician, we're going to skip that part because it's not very relevant for us. So that's data versus information. Let's define the term big now. Let's talk about big data. The term big shifts a lot over time. What was big 10 years ago is pocket change today. I'll give you an example. One of the eBay companies that I worked for had a 10 terabyte enterprise data warehouse a number of years ago. And back then, we used top-of-the-line Oracle database. We used top-of-the-line Sun hardware. We used some pretty serious storage devices from EMC. It was a pretty big installation back then for a 10 terabyte data warehouse. I can buy one off-the-shelf Intel-based server today and park 10 terabytes of data there. I could probably, if I work real hard, stuff 10 terabytes or something in the neighborhood of 10 terabytes into a Postgres database, a single instance Postgres database today. So that is definitely not small data today. So the lesson here is that the definition of big depends on the time context a lot. And it's always, we should keep it in the back of our head when we look at papers, books, and things like that, because to look at something that was published 5 years ago that defines what was big back then, it's not big anymore today. To me, one of the things that rules out the data being big, if you can buy an off-the-shelf appliance or a handful of off-the-shelf appliances and solve your problems that way, the problem you're solving is not a big data problem. Because true and honest big data problem cannot be solved by just buying a handful of off-the-shelf appliances. That's just, by definition of the term, big data problems are larger than that. And typically the way we solve big data problems is by using some technology that relies on clustering, sharding. Basically, in essence, we are going to take a large data set that's so large it's unmanageable on a single machine. We're going to break it into pieces, and we're going to apply a hash function to those pieces, and based on the value of that hash function, we're going to distribute these pieces of this data set to different machines and take advantage of the parallelism. And that's regardless of whether we're talking about a database or any other technology. The essence of scaling out is the same. that's the root of how we manage the big data problems. So if we're not talking about something that scales out by means of clustering and hash distributing the data in some form, we're not really talking about big data. IBM has a very nice definition of what big data is that I happen to really like. I get no credit for it whatsoever, but they define it as something that scores high on volume, velocity, and variety. Velocity basically means that things flow real quick and they change quickly. Variety means that you have all kinds of data in all kinds of different formats. And volume is, it's big, it doesn't fit into a single instance Postgres database. So, so that's why big doesn't necessarily mean just volume. Typical big data problems have a variety of data, and they have a data that changes all the time. In some cases, even in real time. The format of the data might change in real time if you think about things like that are machine-generated, Internet of Things, those types of buzzwords. So for something to be true and honest piece of big data technology, it has to process high volumes of data. That's an absolute prerequisite. The data flows at high velocity. Typically, for us to be able to accumulate high volume of data, our pipe has to be pretty big. And it has to score high on variety. You don't have to have all three. I would relax this definition by saying that if you score pretty high on at least 2 out of 3, you have a big data problem. So it's not a very rigid formal definition, but it's always good to think along those 3 dimensions and not just one when you're assessing whether something is a big data problem or not. So as we have learned in practice with a few customers of one of the companies I used to work for, security information and event management at scale is indeed a big data problem. So for the solution that we were working with, we were collecting logs from various devices like firewalls and web proxies, and I'm sure people in this room know very well what kind of devices are typically collected from. So arguably even better than me, because I have a relatively small slice of it. And compliance was a pretty serious requirement. Other forms of analytics are definitely something that needs to be done, but if you can't meet the compliance requirements, you kind of don't meet the baseline, you don't get to play. It's like the minimum requirement for you to be able to sit at the table and play is you have to meet the compliance requirement. Now, once you've met the compliance requirements, that's when you start competing with other vendors based on how good your analytics is. But if you can't meet the compliance requirements, no one's going to consider you seriously. So for a large organization, it's a healthcare and health insurance vertical organization that we talked about. We had a volume of data that was in the petabytes. For the retention intervals that they required because of their compliance requirements, they needed petabytes. And this is a legit, serious big data problem, because you can't stuff even single-digit petabytes. You can't stuff them on one box. You can't really stuff them on a handful, like half a dozen vendor appliances. Chances are it won't pan out well. So when it comes to velocity, well, firewalls and web proxies generate event streams in human perceptible real time. As the humans keep doing clicky clicky, these events are happening. So the velocity is clearly comparable to that of a high traffic website. Why am I bringing high traffic website into this? Because in most of the big data books, having event stream or a click stream from a high traffic website is considered a textbook example of a big data problem. So to me, collecting security event data is very, very similar and very, very close to what you would do for a clickstream of a high-traffic website. It's at least the data itself may be different. The meaning of the events will be different, but the mechanics that you can use to collect, process, report you can reuse the same technology because it's data that flows at similar speed and possesses many of the very similar characteristics. So variety. Variety is definitely a challenge for the security use case because well, back when I was at Facebook, variety was clearly a problem because it's a very large website with a lot of features developed by a lot of different people and teams. But if you're a little less ambitious than a company like Facebook, arguably you don't have all that much variety. After all, it's your website, you've built it, it's your application. Of all people, you're supposed to know what data is being generated. Doesn't always happen this way, but at least in theory you should. When it comes to the security devices, well, we patch firmware, we update versions, we bring new vendors, we decommission old hardware. The formats of the data change. What is being logged changes. And that's, while the rate of change may not be all that high compared to a website that gets a weekly push, the problem is that when that change happens, it happens from the vendor end. You don't necessarily get the warning ahead of time that we're about to change the log format that you're using to produce your reports and analytics. It's always good to vet it and see if the new version of the firmware is going to blow away whatever analytics you've built, but sometimes these patches come as an emergency. You don't get the luxury, so you'll have to live with your reporting and analytics broken for a period of time until you adapt. So that variety definitely gets us in trouble when it comes to the big data security use case. Technology is big and small. So if we have a single box appliance, that does not make scaling very easy. That's, to me, ultimate small technology. Now, for practical terms, small could actually be, ironically, pretty big. Yahoo at one point has built world's largest SQL Server Analysis Services machine. They have built the largest ever box to run Windows operating system because SQL Server Analysis Services only runs on Windows. And they have loaded more than a petabyte of data into that one box. I have had the benefit of working with people who did that at Yahoo. Take my word for it, you don't want to go that route. Microsoft's a great vendor and a sponsor of this event, but you really want Microsoft on board with something like that, and an exercise like that is both difficult and expensive to pull off. So scaling up to the largest box you can buy is definitely the dead end in evolution of the system, in my opinion. You don't want to go that route. So as volumes grow, you end up sharding the data. Sharding the data manually is quite painful. When I used to work at Facebook, we ran, at the time, over 130,000 MySQL sharded instances that functioned as essentially a very large key value store. So the schema, the relational features of MySQL were pretty much unused. There was a piece of middleware that was sitting in front of those. There are over 200,000 MySQLs at this point now. So there was a piece of middleware that was also clustered that sat in front of it that routed the data to the appropriate MySQL instance, and they were replicated to different data centers. The gentleman who ran this very large MySQL installation is the guy who wrote the O'Reilly book on MySQL cluster, Harrison Fisk. There are very few people on the face of this planet who know MySQL as well as he does. And not many companies get to hire people of this level of talent. So if you are going to go big, doing the sharding manually is a difficult thing to do. And you should probably look at a product that does the sharding for you, that eases a lot of these pains. Typical problem, once you have sharded the data, reconstructing it back becomes a gigantic pain. Like once you want an integral picture of all of those things that you've sharded, spread out, you really want the product to be able to do that. Because the product cannot reassemble this data from different shards and give you an integral picture. You're probably not getting your money's worth, because it's probably not that great. So a true big data solution will give you this sort of auto-sharding functionality where it will shard things for you when you pour data in, and when you run a query, it will query all those different shards and bring the data together and give you the picture. Of course, your question has to be reasonable. If you ask a totally unreasonable question of summarizing the entire petabyte of data in some really unusual way, it just won't happen. Big data is not magic. So let's look at, we were talking about technologies in general, and I stayed away from the specifics intentionally. I will concentrate on databases and non-databases technology. This is where it gets a little fuzzy, and I think needs a bunch of clearing up. So databases are good fundamentally at one thing. If you have a very large volume for our purposes, for analytics purposes, they're good at many things, but the thing that they're good at that's relevant for our analytics purposes is this. Say you have a large pile of data, and you want to fetch a small subset out of this large pile, like this, very quickly. That's low latency access to data. If you have laid out your data on disk in a way that makes it possible, a database will do it for you. There's no such thing as low latency access to the entire petabyte of data. If the task at hand necessarily requires sifting through a very large pile of data top to bottom, it won't happen in low latency no matter what technology you throw at the problem. So databases can be broken into transactional and analytics. So transactional databases are not very interesting for us for the scope. Traditional relational technology largely. Recently, there's been some non-relational entries. Fundamentally, the task at hand is I'm running a short transaction, has to happen instantly, has to persist this data in a durable fashion so it doesn't get lost, and has to be able to resolve issues with concurrent access to this data, where multiple concurrent inserts updates may be happening. Again, that much for the transactional databases. We're talking about analytics. Usually, there are some trade-offs that the designers of the database engine take. So databases that do transactions well don't do long-running analytic queries well. Databases that do long-running analytic queries well don't do transactions well at all. That's an unfortunate fact of life. And Michael Stonebreaker, who teaches databases at MIT and is a very well-respected database scientist who I admire and respect a lot, has many times recently said that the general purpose database is dead. In that, if you're doing something that's not trivial, you should pick a database that fit for that particular purpose. The non-database systems are the likes of Splunk and Hadoop clusters, and we're going to spend a bunch of time talking about what those things are good at and why they are what they are, and what they're not good at, and when you shouldn't really be using them. We just went over transactional databases and analytic database. So I find analytic databases, especially of the MPP variety, massively parallel, scale out, to be quite useful for the security use case. But there's a trick to it. Sort of out of the box, relational database cannot be easily married to the security system that has firewalls and logs. There's a whole thing that needs to happen that we'll cover in a second. So to make long story short, once you have consumed your data, cooked it to be a final product that's ready for consumption, you can publish it to the relational database and use off-the-shelf business intelligence reporting technology instead of a very expensive and very feature-limited security-oriented product. So that's how you can get good mileage out of the relational databases, in my experience, for the security use case. So low latency access to data, as we said, no such thing as sifting through the entire petabyte in low latency. It just doesn't happen. So how do we physically facilitate this low latency access to data? What are the tricks that enable the database to do that? One is partitioning. We can partition there. Unfortunately, like many terms in the database industry, the term partitioning is inherently ambiguous. So the partitioning that I'm talking about is sometimes called horizontal partitioning, which you can also flip the axes. So what's horizontal to one person is vertical to the other, unfortunately. But I'm talking about, we have a year worth of data. We break a year worth of data into monthly chunks, and we can access each chunk as if it were its own table. That type of partitioning is divide and conquer, ends up being extremely useful in most analytic databases. You can have multiple layers of partitioning if your database is good, in that you can partition it by month and then further sub-partition it, possibly by some other dimension. And by eliminating a lot of I/O, you can speed up things dramatically. A database that ran out of performance and ran into the wall will typically have plenty of spare CPU cycles, and in many cases it will even have plenty of memory. What it won't have is the I/O channel, because once your I/O channel is maxed out, for most traditional databases, you're out of luck scaling. So for that reason, anything and everything you can do to minimize or eliminate I/O, you should always do, even if you're doing it at the expense of CPU and memory. Because a database that ran out of performance has CPU, has memory, has no I/O. Indexing, I'm pretty sure most people are familiar. Building an auxiliary structure that allows you to find relevant records. Databases commonly use height balanced B-star trees for that. The other alternative is to store everything in a columnar format and store it sorted, which is like essentially storing everything in a quasi-index, if you think about it. So the likes of Vertica, Redshift, various relational column store databases do things this way. The advantage of this is you don't actually need to build any indexes. Vertica does not support indexes. But the columnar storage itself, in its performance characteristics, is similar to an index. Storing data in sorted order, storing data in columnar format, depending on who your database vendor is, one or more tricks will be available to you. But all of these tricks are fundamentally aimed at eliminating I/O by sacrificing some CPU performance and some memory and getting the performance out of the database this way. That is pretty much the name of the game for scaling analytic databases. Now, so far I talked a lot about relational databases. I have to tell you the truth, that while relational databases are good and important, there are other databases, key value stores, the likes of Apache, Cumulo, Cassandra. They scale pretty well. We used HBase at Facebook, and we had a very large HBase. Apple uses a 75,000 node Cassandra database, according to people who work there. They can be scaled to very, very large volumes, but unfortunately, the thing about key-value databases, when it comes to analytics, they are a one-trick pony, in that when you do a data modeling for Cassandra, the advice is you should design your data model for the read, optimize it for the read. And that implies that there is a particular read that you can do, and that's kind of it. And you don't get to do things like joins and whatnot. So there's going to be a number of things that you will be able to do in terms of read. But you will be constrained by the data model that you have designed, and you won't be able to really step outside of these constraints. So it's a limiting approach, which for analytics, especially in the security use case where we don't know what we're going to get hit with tomorrow, having a system that is constrained on what you can do, in my mind, is not a very good thing. Because that lack of flexibility is definitely going to be very limiting for anything security related. We can have document data. We also have document databases, and I have to especially point out Elasticsearch. And we played with Mongo when I was RSA. Mongo is a pretty decent document database. The unfortunate downside of a document database in general is that unless you query one of the indexes, a good document database will support ultimately indexing for text, right? So unless you're querying the index itself and the index only, you will be parsing the data when you read it. And parsing is never cheap. So, the document database is also limiting in a way, in that you have indexed certain things, and those things will work pretty fast. Whatever it is that you haven't indexed will be pretty painfully slow. The other unfortunate part about document databases is a lot of the indexing technology is tailored towards natural language text. And what we are dealing with for the security use case is machine-generated, highly repeatable data. And it doesn't quite possess the same characteristics and the same degree of structure as natural language text. So the choices, the design choices that were made by the designer of the document database to index documents in natural language text may not be the most optimal design choices for machine-generated log data. We'll skip the slide. So, non-database systems. Why do we even need them? Like the likes of Hadoop and so on. Well, don't try to use Hadoop for a reporting solution. Don't try to use Hadoop instead of a database. Take my word for it, it will hurt a lot if you do. I have seen it time and time again. Hadoop is not good at things that databases do at all. So what these non-database systems are good at is processing data into information. Things like parsing the logs. Things like basically doing all kinds of transformation on that data. So getting you from the log to a nice structured data set that you can throw over the fence into an MPP database is what a system like Hadoop can do very effectively. And some companies use Hadoop, or I should say abuse Hadoop for a quasi-reporting or a database-y solution at scale, simply because there is an upper limit to scalability of an MPP relational database. The best massively parallel relational database will probably scale up to about, I want to say, 300-ish nodes. Past that point, two things start to happen. One is the licensing costs at that point are dipping into the double-digit millions of dollars. Not a lot of companies will be able to spring that kind of money, even for their main analytics system. And very few will spend it on security. I mean, it'd be difficult to find a company that spends double-digit $1 million on just a SIM solution, right? I don't think that these types of sales happen very often. So licensing cost will limit severely the ability to scale a relational MPP database. The other thing is the technological constraints of the database itself. You have enough relational database, replicates everything, pretty much two-way. So you have enough disks, you're going to have problems. At any given point in time at 300 nodes, you will have nodes that will be down. Well, MPP databases don't like that. Hadoop replicates everything three-way, so it's a lot more resilient to this type of failure. So what is the essence of Hadoop? HDFS is a distributed file system. Scale out, store a whole bunch of data, store very small, relatively small number of large files on a cluster. MapReduce is an execution engine, so it allows you to process the data that is stored on HDFS. There's an entire ecosystem of tools that are built on it. Two most relevant for this purpose are Hive and Pig. Hive allows you to run SQL against a pile of files on the HDFS. Pig is more loop-oriented. If anyone knows COBOL programming, think COBOL without the ugly syntax. Pre-SQL type data processing. So HDFS is a one-trick pony. It hates small files with a passion. It's designed to store a small or manageable number of very, very large files by splitting them into chunks and scattering them across. So everything gets replicated three-way. Generally, if you manage your Hadoop HDFS well, you won't lose data. But it's a highly inefficient solution at low end of the scale. So if you're talking about 5 to 10 machines, forget HDFS. It's a very ugly way of storing data at that end of the scale. MapReduce, this is like the classic MapReduce example that does the word count. It's called shuffle sort. I stole it from one of the universities. To make a long story short, you define a mapper function and a reducer function. And the mapper function processes everything sort of in line. And then the reducer condenses multiple rows into one. In the interest of time, I'm not going to dig into that deeply. Hive is a very useful tool once your data is in somewhat of a relational format. It understands most data formats that are common in Hadoop. It allows you to run SQL against files, much like very early products before relational databases gained prominence did. We ended up using Hive for a security system that I worked on. It has some redeeming qualities. It will scale above and beyond where MPP relational databases will break down. But I doubt that many people in this room will be building a system with more than 300 nodes. So that upper end scalability is probably not a concern. It'll process volumes of data that are beyond reach for a lot of MPP databases. But again, who's going to do 120 petabytes of security data? Probably not a lot of people outside of the government agencies. Being a file-based query engine, it can cope with file file format changes much easier than a relational database would. So that data that keeps changing, it's easier to deal with it in Hive than it is in a relational database. Downsides, inefficient at low end of the scale, just like any other Hadoop solution is. Up to 50 nodes, I will always beat Hive by at least an order of magnitude, generally 2 or 3, with a relational database that runs on an MPP platform. For complex queries, I will beat it by a lot. And for very complex queries, there's no contest because Hive won't do them. So, security data. Well, we collect a bunch of logs. APIs are often vendor-specific. It's painful. So one of the things we could do is we could rely on the data traveling down the wire and use something like Bro, big data from the wire, and store it in the log format that we control, not some vendor. And that will allow us to throw it into Hadoop. And that will, TCP/IP doesn't change as frequently as log formats by the vendors. So this will make a lot less brittle system. And devices have to interoperate, so a lot of the network protocols are standard and will remain standard for a while. So, and this way you also don't have to deal with proprietary APIs. Unfortunately, what breaks this rosy picture is sometimes some things don't travel down the wire. If I have an Oracle database sitting somewhere and it writes something that happens inside the Oracle database to the log, that data won't travel down the wire unless I pull it out myself. So not everything can be done through packet captures and parsing metadata out of packet captures and storing them in my analytic system. So there will always be a use case for parsing the log. So Hadoop enables you to reuse your legacy log parsing technology very nicely by something called Hadoop streaming. Hadoop streaming basically allows you to put just about anything into Hadoop that reads from standard in and dumps output to standard out. And it allows you to scale just about anything that way. So if you have, because dealing with a whole bunch of legacy formats is quite painful. So Hadoop streaming is a very useful tool. If you want to go to Hadoop and you have a reason, and you're going to be building a large Hadoop system, you can take your existing log parsing technology, wrap it around with Hadoop streaming, and scale it that way. You'd have to install it on every node of the Hadoop cluster, but that will allow you, Hadoop will take care of the difficult aspect of having to orchestrate things and doing that distributed network programming that's inherently difficult to do. The whole thing about Hadoop is distributed programming for the rest of us. Like, I won't be able to write a server that works in a network distributed environment without screwing it up majorly. I'm just not the guy. I don't have the skill set. But I'll write a mapper and a reducer and throw it into Hadoop, and it will do things for me. So that's the redeeming quality of it. It makes it easy. So there's something called packet pig. It will allow you to process packet captures in Hadoop. So you can throw your pcaps into Hadoop and process them there. So basically, by collecting this data and parsing it, we are turning data into information. Because data comes in a way that's convenient for your firewall to log, for your web proxy to log, for whatever software that logs it, to dump it, right? It's a printf statement somewhere in some code. We parse it, we process it, we summarize it in certain ways that make sense for the questions we're going to ask. So what your Hadoop system will do is it will take data from this format that's ill-suited for answering the questions you want to ask, and you will process it into a different format that will make answering those questions easy. And that's largely the point. And then once you have processed your data into this format that makes it easy, you can publish it to a query engine that will facilitate answering these questions like a database. So that is sort of the pattern. The design pattern here is collect data in whatever ugly format it's in, process it, reorganize it in a way that facilitates answering the questions you want to ask, publish it to an engine that makes answering those questions easy. So Hive is not a bad tool for processing this data, what in the data warehousing and data management we consider ETL. It'll do a full table scan every time you query it, but if the task at hand requires processing all of it anyway, so be it. Do not abuse Hive for a database engine, as I said before, and I'm repeating it probably for the umpteenth time because I have seen it time and time again when people did it and it hurt like hell. Treat your relational database as a dinner plate and silverware and a fancy one. Don't put crap in a relational database. It'll be a horrible experience. Crap in, sift through the crap, find what you need, get the good stuff, put it on a relational database once it's a final product. You'll be a lot happier because it will work a lot better. The other redeeming quality of a relational database is that any halfway decent business intelligence product will integrate with a relational database. If a business intelligence product does not connect to a relational database, it's a joke. It's not a product. So publishing your data into a relational database enables you to use all kinds of products, like your Tableaus, your MicroStrategy. If you work for a big enough of an organization, chances are you have at least 2. Use it. You probably have a site license. All the pretty graphs, trending over time, all of that stuff that a security vendor might charge you a premium for. In the business intelligence world, this is standard functionality. So use it. With this, I'd like to open for Q&A.
What is your sense as far as timeliness for doing this sort of thing for security purposes? I mean, it seems to me that where we're looking at the strength here is from a forensics perspective, not any sort of reaction or response perspective. Is that your sense as well?
So usually this covers only one. If you look at something called Lambda architecture, it has 2 legs of it. One leg is the batch processing. So this is what we covered in this presentation. Typically, you would go through these large batches of data. You would extract some knowledge out of it, and you would publish it into a different system that works in a much more timely manner. So that we didn't cover here. So you could build streaming systems using Kafka and Samza, for instance. There's a number of technologies like Storm you could leverage. So you would use this to look at historic data. Say you are scoring your data based on how risky it is. So you can compute the coefficients for your scoring model based on historic data in your system that has long-term memory, and then you ship those coefficients to the system that sits on top of the wire and scores events as they fly by and flags them. And then you would constantly revalidate that on the back end. So the system that does it in a very timely manner is a whole different animal that's not covered in this presentation. They complement each other. Please.
Yeah, so I was just wondering how much machine learning techniques used in the big data context.
Machine learning is machine learning is one of the tools that we have in our toolbox. It is useful for certain things. Basically, if you want to classify things, it's one of the things that machine learning can do quite well. So unfortunately, a lot of machine learning techniques won't give you an explanation. It's kind of a black boxy thing. They won't give you a score or tell you yes, no. Statistical learning has to be a little more user-friendly in that you can actually explain why. So I see people using statistical learning mostly because once we have given an answer yes, no, someone comes back and says why yes or why no. With statistical learning techniques, we can throw a whole bunch of stats on the board and say this is why. This is not to imply that machine learning is not useful. It just, like any technology, it has its limitations. And both statistical learning and machine learning are heavily intertwined. Unfortunately, a lot of the apparatus for machine learning is not scalable. So a lot of the software that you use for machine learning would require you to either sample your data or condense it to a very high degree. The one thing that I didn't cover in the presentation that's happening right now, there is something called Spark that is becoming increasingly popular. And it can run as a cluster on its own, or it can run inside a Hadoop 2.x cluster. And it gives you a whole bunch of machine learning algorithms already implemented. And it will work on a very large scale. So if you want to get your feet wet on large scale, I would encourage you to look at Spark, because it's a very, in my personal opinion, that's probably the future of the intersection of big data and machine learning is probably somewhere in the vicinity of Spark.
You mentioned Elasticsearch a couple times. I'm using that in a small project. We're dealing with about 60 gigabytes a day of logs. It seems to work pretty well. I was wondering if you had any particular opinions on it, or...
I like personally I like Elasticsearch better than MongoDB.
Yeah.
I find it to be, in my opinion, it's one of the best document databases on the market today.
Yeah.
So, with the caveats that the indexing scheme is originally tailored for natural language search rather than logs. It can be adapted for logs or highly repetitive machine-generated data. But with that caveat, I mean, you can do a lot worse than Elasticsearch today.
Yeah, I'm loaded up using Logstash, and what we found is that while I can write Python programs against it, for example, that will read the digested logs and generate a table with more information-y tables, there's limits there, and we're debating whether we should take that digested data, the secondary level of the data, and throw it into a relational database of some kind. It sounds like you're validating that thought.
The Elasticsearch is very good at what it's supposed to do, which is certain things. It will run essentially equivalent of basic single table queries in a relational database with fancy textual indexing. So think of it, if we were to compare it with relational database, it's something that can do single table queries and very, very fast queries with like predicate on them. Mm-hmm. Outside of that use case, it kind of doesn't do a whole heck of a lot. So if you need to cross-reference your data with something, if you need to do additional lookups, if you need to do some kind of enrichment or blending of your data, Elasticsearch isn't the tool to do that. Not because Elasticsearch is bad, it was just never designed to do that.
Okay.
So in that case, you would process this data, because your documents probably have a lot more than you need. So you're going to extract what's relevant for answering your questions out of your documents, publish it in some strongly structured tabular format in a form of one or more tables into your relational database, publish other data that you want to cross-reference and link to from other data sources into your relational database, and query it that way.
Okay.
Okay, I think I ran out of time. Thank you very much for attending my presentation. Appreciate it.